Welcome to the Quantum Gold Rush. Today, we're discussing quantum computing. Imagine facing some of humanity's most daunting challenges. Designing a catalyst that can efficiently capture carbon dioxide from the atmosphere, thereby reversing climate change, or simulating a new drug molecule at the atomic level, reducing drug development cycles from decades to months, or cracking the encryption systems currently used by all banks and militaries. These tasks are beyond the capabilities of today's most powerful supercomputers, requiring hundreds or even millions of years, effectively tantamount to mission impossible. However, a new era of computing is dawning, with the potential to transform these impossibilities into possibilities. This is quantum computing. To help you understand the disruptive nature of quantum computing, we can use the metaphor of a library. Imagine you need to find a specific piece of information in a vast library containing billions of books. A classical computer, even a supercomputer, is like a swift librarian, having to leaf through each book one by one until it finds the answer. A quantum computer, however, exploits the unique properties of quantum mechanics to read every book in the library simultaneously. This may sound like science fiction, but it's possible. This capability stems from two core quantum principles. One is superposition. The fundamental unit of a classical computer is a bit, which is either 0 or 1. The fundamental unit of a quantum computer is a qubit, which can be simultaneously 0 and 1, as well as an infinite number of possible superpositions between 0 and 1. This is like a librarian being able to open every page of every book simultaneously. The other core principle is entanglement and interference. When multiple qubits are entangled, their states become instantly correlated, regardless of distance. Through clever algorithmic design, quantum computers can exploit this interference effect to cancel out incorrect answers and highlight the correct one. It's like reading all books simultaneously. All invalid or incorrect paths disappear, leaving only the one that leads to the correct answer. It is this exponential power of parallel computing that gives quantum computing the potential to revolutionize fields such as pharmaceuticals, materials science, financial modeling, artificial intelligence, and national security. Experts predict that by 2030, the total potential market size of quantum computing could reach approximately $65 billion, and its disruptive impact on downstream industries could be worth trillions of dollars. This quantum gold rush has attracted countless capital and talent, and a number of ambitious companies have entered the capital market. However, for ordinary investors, this field is both alluring and extremely obscure. Some companies have seen short-term surges, but their financial data lacks investment value. Faced with such a specialized technology, investors can only rely on narratives and confidence to believe these valuations, which is clearly a high-risk speculative behavior. Therefore, it is necessary to clarify this technology field so that ordinary investors have a certain understanding of the risks involved and avoid being blindly betting on rumors. Different technology paths are like different gold mining tools. Each company has its own unique survival strategies and significant risks. We will deeply analyze a series of publicly listed companies related to quantum computing to create a clear investment map. We will peel back the complex technical shell and examine each company's business model, core competitiveness, financial status, and valuation level. More importantly, we'll clarify which are the true quantum gold mines, which are the shovel and jeans vendors, and even which are merely red herrings that look similar but are actually in a different arena. Our goal is to enable you to make clear and informed investment decisions in what may be the most important technological revolution of this century. Before delving into specific companies, we must first understand what's under the hood. Investing in quantum computing companies isn't just about investing in a business. It's about betting on a specific scientific paradigm. Currently, there are 4 major approaches to quantum computing technology, each with its own unique strengths and weaknesses, like different engines designed for different races. The first is superconducting qubits. This is the current focus of tech giants like Google and IBM. Imagine scientists creating tiny, artificial superconducting circuits on a chip. When these circuits are cooled to temperatures near absolute zero, colder than outer space, they exhibit quantum properties, becoming controllable qubits. Their greatest advantage is their high computing speed. Quantum gate operations, equivalent to logic gates in classical computing, can be completed in nanoseconds. Furthermore, it can leverage decades of mature semiconductor chip manufacturing processes, theoretically making it easier to scale production. However, these artificial atoms are extremely fragile and extremely sensitive to even the slightest disturbance in their environment, such as temperature fluctuations, electromagnetic waves, and vibrations. This causes them to quickly lose their quantum properties and produce errors, a process called decoherence. Maintaining their quantum state requires large and expensive ultra-low temperature refrigeration equipment, which makes the entire system extremely costly and bulky. Rigetti Computing, stock symbol RGTI, is a major player in this technology, a publicly traded company, along with tech giants like Google and IBM. The second type is trapped ion qubits. If superconducting qubits are artificial atoms, then trapped ion technology uses the real thing. Scientists use electromagnetic fields like an invisible cage to trap individual atoms, ions, in a vacuum. Then, precisely tuned lasers manipulate the quantum state of these ions, turning them into qubits. This method offers exceptional precision, like a fine Swiss watch. Because each atom is a perfect creation of nature, they are identical and extremely stable, maintaining their quantum state, coherence time, much longer than superconducting qubits, which means lower computational error rates. However, the main challenge lies in its relatively slow manipulation speed. As the number of qubits increases, the laser system required to precisely control each ion becomes extremely complex, making scalability a significant engineering challenge. The main players in this technology path, IONQ, stock symbol IONQ, and Quantinuum, a subsidiary of Honeywell, stock symbol HON, are leading the way. The third type is quantum annealing. This is a unique type of quantum computer. It is not a general-purpose computer that can solve all problems, but rather an optimization master, specialized for specific problems. We can use a topographical analogy. A complex optimization problem is like a map with peaks and valleys, with the goal of finding the lowest valley, the optimal solution. Quantum annealing machines, through the quantum tunneling effect, can pass through the peaks directly, rather than climbing over them like classical algorithms, thus finding the global minimum more quickly. This approach is somewhat like time travel through a wormhole, allowing one to quickly reach a desired era. Its greatest advantage is that it has already been commercialized and can solve complex real-world optimization problems today, such as logistics routing and financial portfolio optimization. Compared to general-purpose quantum computers, it is more tolerant of environmental noise. However, its drawback is obvious. It is only a limited technical tool during a technological transition period. It cannot solve problems such as Shor's algorithm, used for cracking encryption, which require general-purpose quantum computers. Whether its long-term potential will be surpassed by general-purpose quantum computers is still under intense debate. The main player in this technology path, D-Wave Quantum, stock symbol QBTS, the pioneer and undisputed leader in quantum annealing technology. The fourth approach is photonic quantum computing. This approach uses the smallest unit of light, the photon, as a qubit. Through a series of optical components such as beam splitters, phase shifters, and detectors, the quantum state of the photon is manipulated to perform calculations. The greatest potential of photonic quantum computing lies in its potential to operate at room temperature. If achieved, this goal would be a game-changer, as it would eliminate the need for large, expensive ultra-low temperature refrigeration systems, making quantum computers miniaturized and affordable. While promising, this is a relatively immature technology path. Precisely generating, manipulating, and detecting individual photons, and preventing them from being lost during transmission, presents enormous engineering challenges. Currently, there's still a long way to go. A major player in this technology path, Quantum Computing Incorporated, ticker QUBT, is a representative public company in this field. Understanding the differences between these four engines is crucial. When you invest in a quantum computing company, you're not just investing in its team and business plan. You're also making a bet on the technology's trajectory for decades to come. Okay, that's all for now. We'll continue next time.